This is example number 5, shear joints for eccentric loading. This particular example, we have this steel plate, 3.5 inches times 5 inches, has this particular loads applied at the end. And this is 0.20 inches thick. Uh, and it's cantilevered to this bar, to steel bar, and this is a quarter inch thick. It has uh, four bolts, 3/8 24 unified fine series grade 5 bolts. They are tightly fit and have no preload. For a design factor of 1.04, determine if you recommend the design, and it gives you the yield strength of the steel plates, this particular steel plate. Okay, so the first thing you want to do is you want to find the fastener areas. You want to find everything you want from the problem. I like to do always just do a coordinate system. I place my coordinate right here. So this is my 0, 0. Okay, this is my 0, 0. And so this is 0, 0. And then from here, the distance from here to here is 2. From here to here is 2. Two in this direction, 0.75 up. And then this one is 2 inches, 2 inches, and is 0.75 going up, and so on and so forth. You can find what each one of these will look like. 175, and this is 0 because it's in the same axis, and the distance from here to here is 2.5. So just fill this information in. Secondly, we want to use the table 8.2 and 8.9 to find your bolt properties. All your bolts are the same size, so your problem says this is the type of bolt that you want to use, right? So you can go to your table 8.2 and find which bolt is, and I just gave you here the information that we are going to need: the tensile, the root area, and the proof strength and the shear proof strength. I calculated this. Remember, this is SP divided by square root of 3, and this comes from table 3. This information right here, 8.9, sorry. Once I have that information, let's find the center of coordinate where this is located. I have the areas, so you can see. Okay, just want to point this out that the area I'm using here to calculate this is pi d squared divided by 4. Okay, so that's the area I'm using here. I am not using any of these areas. You could have used it. You probably got the same answer. But this is the area I'm using. I'm not using the tensile area. I'm using the total bolt area. And that's the information you get. Then you just do the multiplication between this and this. You get these values. At the end of the day, these are the values I really care for. These additions. You can do this very easy in Excel. Even in MATLAB, this is a very easy, simple way to do this. I like to do this in Excel, but I can do tables. Then you add all this. The total area is 0.4418 inches squared. Then here, AI, XI, this is addition is this. You add this, you divide it, this gets equal to 1. You can see, kind of makes sense, right? This pattern is symmetric in this section, in this direction, so this is 1. And your Y will be a little bit different, it's 1.2, so that is located right there in the middle. So it kind of makes sense what I have so far, and so now we can move on. Okay, so let's continue. Then now what you want to do is you want to find the coordinate about the centroid. So I want to find about this centroid, what are the coordinates each one of these points. The best way to do this is you take your centroid, you subtract this value minus this. I'm sorry, you subtract these values. So every value you have here, subtract 1. Every value you have here, subtract this value. Once you do that, then you can find this is the new coordinate system I'm going to use. Your d of x, this is the distance. I'm using this to find this distance. So um, remember, for I need my r, right, for my moment. So to find that distance, I have my dx and I have my dy. Basically, it's going to be the same distance as here. You can see I'm using the same values, so those will be my distances. And actually, they should be all positive. The distance should be positive. These are just the coordinate systems. So then you find your r. Your r is found by taking the square root of dx squared plus dy squared. Then your angle is the degree. How I calculate this, remember, uh, this is 1. So you're located here. Let me bring this picture in the next segment so you can see how I evaluated this. Um, so this is 1, right? So the coordinate for 1 is here. And this is my angle. I like to use always from the horizontal. Okay, this is the angle. I use this angle right here. Okay, you can use minus sign also, that would have worked, but that's the angle I used. For 2, then you go from here to here. I'm looking for this angle right there. Okay, and so on and so forth. You can look at the figure how we derive this, and that should be quite straightforward. This angle uh, to coordinate uh, to angle 3, that will be the angle 3 from the horizontal, and then angle 4, that will be from the horizontal, and so on and so forth. Okay, so you can find those angles and show that this is what you're going to get. So from here you find your cosines or sines. Once you have your cosine and sine, the next thing you want to do is you want to make sure you find your uh, resolve all the laws of the centroid. To do that, multiply by 1.1 or 1.2. These are the loads that act on the center. So if I move everything, shift everything here, these are the loads I will be using for my analysis, okay, my study. Okay, so now that we have everything, now we can move on here, and then we're going to find px and py for the load acting in each fastener. I call it alpha I. Just easier for me to do that, but it's all the same. This is the blow bolt area. Then I'm going to say take the summation of this. Maybe the bolts are different, and this will give you a different value. You divide this, and then you take each one of the loads and multiply by times alpha. Okay. One thing that should be important is if I add these numbers should give me exactly what I have here. Same value. Okay. That's a check. Now, if I do what's the load Fx and Fy acting because of my moment, we already found this guy, so you square this, multiply a times a squared. Then I call this beta, where you basically are taking a ar divided by ar squared. So this is ar squared. Maybe there's another item missing here, ai ri. You could also add that, just do it directly. But this is correct, okay? And then from once you have that, you take your p, okay, you find your new p, m times beta, that gives you this, and then you just do cosine and sines, and that will give you your directions. Okay, so having that, then remember this is the summation of x1 plus x2. This is x1, okay? This is this load plus what I got here. That will be the total load I'm going to place there, and so on and so forth. Okay, so this is where I get this from. Your fs is nothing else, the square root of fx squared plus fy squared. and this is how I find this. I'm going to take the maximum load here, and all my analysis will be done by this because all my bolt sizes were the same. If the bolt sizes were not the same, then I will have to check the strength for each bolt individually. Okay, just want to warn you. That's why I just used this bolt, and that is the maximum load acting at bolt number one. So I'm going to analyze bolt number one. So I am basically saying, let me see what happens with this bolt, and I'm going to size all the others based on this analysis. Okay, so I do the bolt check. The first check, it has since this is tight, so it uses the threaded area. If it's threaded area, then this is the area I use. This is my load. This is my shear, and you can see that this is actually satisfied. We are good. It is acceptable. So I move on. Now I find the bearing of the bolt. The bearing of the bolt is given by T times your diameter of the bolt. Remember, this is the thickness. So this is 0.075, and you do this, and this gives you 1.11. Bigger than 1, we are also good. So now you keep on moving on. You want the bearing. Now you want to check the plate members. The plate members, you find the bearing area. First thing is the bearing. Remember your stress. This I found it again, sigma yield divided by square root of 3. So this is 80 divided by square root of 3, just in case how I got this value. Then you calculate how much is your. I converted this to KSI to be KSI to KSI, and this gives you 1.04, and it's not an issue. The last thing you do is do this net section calculation. So you calculate this. This is 0.2. This is the thickness. This is 3. This is so let me just show you. Here in this case, this is 3. This will be all the loads acting in the FY direction, and this is 3.5. This is all the loads acting in the FX direction. So again, this is FX. This is for FX. This is for FY. That's why you see I use FX and divide by this. This is my bearing stress. This is my net section stress. Is quite small, so I doubt this is going to fail. And it's basically a tensile check. And in tensile, you can see that what I have. So this is not going to fail. Definitely it's not going to fail, but this is the interaction equation that I have, and shows that this is good. And I have to tell you, next section check, this is mainly for tensile loads. But however, your load can be applied in either direction. Then you can say, what happens if my load gets inverted? So I can be conservative and assume that my compressive load is my tensile load. Okay. What would you do in the case that this is not safe? If the joint fails, consider changing the bolt sequence. Okay. Maybe the sequence will help. Consider changing the plate thickness or the bolt diameter. That might help you as well. Try increasing the thickness of the plate may address any bearing concerns. Increasing the bolt thickness is going to help you for the bolt strength. Okay, so this completes example number 5.